This presentation is made together with Grzegorz Gruszczyński, who will cover the second part of the workshop, and Szymon Nowakowski, who you already know. And we, of course, want to thank all the institutes in this institution who allow us to give this workshop to you. This lecture is going to give you a short overview what physics-informed neural networks are, what are the pros and cons. So let's start. I will start with a remark that what we'll discuss in this workshop is physics-informed neural networks in a narrow sense. And this is the, actually, if you Google, if you want to find online what physics-informed neural networks, you will find this interpretation of this. So not every neural network which have some injection of physics knowledge inside is called physics-informed neural network in this narrow sense. So this is a little bit of mess with nomenclature, but anyway, the most important is to know what we are doing. And this, in this sense, the aim of our network is very similar to what you did a week ago with Szymon, when you were trying to approximate some complicated function with neural networks, having many data points from this domain. So you had x and y, and you were trying to approximate f, the function of these two values. You could imagine that this function is, for example, temperature in steady state for some system. So what you did last week was this approach with no physics. You had only measurements of the temperature at different x and y's, and you wanted to interpolate the temperature in the whole domain. The other type, like classic approach for this kind of problems, is that you don't have so many measurements. I mean, not at all. Or maybe you need to have some conditions like parameters of thermal conduction and some heat sources and so on. But you have so you have this all physics information, and you compute the temperature field from this information. But this requires that you have really all information required to compute this temperature field in this static steady state. This is a classical simulation of physics. And our goal is to do something in between. Like we have some measurements of these temperatures in some points, and we want to approximate the function of temperature in the whole domain, as you did in the regression task 1 week ago. But we'll put additional constraints that can reassure that our solution actually meets some equations which govern how the temperature is distributed depending on the thermal conductivity, and thermal sources, and so on. So the task is just to recapitulate. We have single system which we given parameters and measurements, and we want to approximate the value of functions of a function in the whole domain in a physically informed fashion. And physics meets and deep learning, they meet in various form. I mean, this kind of problem I said now, this is just of many problems where physics meets deep learning. One of other problems we will not cover here is neural operators, which, for example, are used to, maybe you are familiar with the models for weather forecasting. So instead of computing step by step the time frames of weather by classical algorithm with integration, you have some neural networks which predict the next stage of a system in a meaningful way. So this is area of neural operators, which we will not cover here. We did a little bit of this in our previous workshop, but we don't have time for all of this. Okay, so now let's think a little why we inject physics when we to machine learning at all. So it allows us to do a few things. One is what was shown before, that we don't often with physics we don't need so many data points to interpolate some function, because the physics constraints like balance that the lack of information in some parts of our domain, for example. But also comparing to the standard deep learning model, we may want that our solution keeps certain symmetries which are present in our real system, and there's some conservation laws. For example, if we approximate the fluid flow, we want to have this mass conservation and momentum conservation in our solution. And also some parts of the dynamics. For example, dynamics is chaotic. We want the deep learning model to also show some elements of this chaotic behavior, which is of course maybe tricky. And how we can inject physics to machine learning? We have a few standard approaches, and one maybe most obvious is observational bias, which means that we train the neural networks with only physical meaningful data. Additionally, if we know that by physics laws some maybe symmetries are preserved, then we can augment our data with these symmetries. For example, if we know that by physics laws our system is symmetric with left-right symmetry, then we may flip the input randomly, so to assure that the neural networks see in training data with equal number of left and right images. Another way is to inject our physical knowledge into machine learning is inductive bias, what means that we design the architecture of our model in a way that it preserves, it is close to it's close to the physical. I mean, okay, so in a way that we are sure that maybe some physical conditions are met. The simplest example is convolutional neural networks, if you are familiar with. So a convolutional neural network by design reassure the shift symmetry, so that each patch of the input is, if we shift input, then the output will be also shifted with the same shift. Also, this quite often that we know that some problems is easy to solve in the spectrum space. So then we can operate on spectra, or even implement some Fourier layers inside. And the last way how we can make use of our physical knowledge about the system is learning bias, and it means that during the training phase we penalize not only the difference between approximated values and the real data, and this is how you calculated loss last week in the regression problem, but also we can penalize how our solution violates the physical constraints. So we will see it in a minute, because this is the core of the physical informed neural network. So not only the error in estimation of the function of a temperature is penalized, but also that, for example, the gradient of the temperature does not meet some time conditions. Okay. And the physical informed neural networks appeared, I think, something like 2018. You don't need to, I mean, the point of this slide is to show that the number of papers with physical informed neural networks grows a lot, and it's end here, but it continues to grow as most of deep learning topics. And yeah, it's also able to solve many different equations and many different conditions. So people work on this. One important information from this is also that people developed a lot of tricks, a lot of methods for different kind of equations, what works the best. Today we'll show you the kind of vanilla PINN, so the most basic implementations of physical informed neural networks. In your real work, you probably should look at the more recent developments on this, and we'll point to some of them during our workshop part. But just to not do too much at once, we will show you quite a simple version of PINN. And using also, so you may imagine that it's not, PINNs usually are not plug and play, that you have it work for all your problems, but unfortunately you need to look browse literature, and if your problem is not really easy for neural network, then you can browse the literature and look for the tricks that people developed. So what can we do with physical informed neural networks? The most obvious solution the most obvious thing that I already told you about is that we solve partial differential equations, knowing parameters of the equation. This is a weak point, so we need to know the parameters in advance. We find a solution and some measurements or initial condition. We can find the solution of the function we are looking for. Here I will use the U which is you know, the velocity of the flow field is typically given by u. And this is okay. So maybe you may think about this first bullet point as that you know only initial conditions, and this is also possible with PINNs, but that's not what PINNs usually are used to. The big strength of PINNs is that it allows to easily implement some measurements that we know of to our system. So we know the equations, we know some measurements, and we are able to approximate the function, the whole domain, in a physically informed fashion that at the measurement points is equal to our measurements. And the other strength of the PINNs is that it can also solve inverse problems. So we can know some values, some measurements, and equations, but we can not know parameters, exact parameters, and we can estimate both the solution and to find the parameters of the system. So, for example, we can in the last notebook that we'll work on today, Grzegorz will show you how to find not uniform heat conductivity by knowing the temperature and measurements in space. And it also can give us data efficient representation, function approximation. So at the input of the function, we give the time, if we need a time, and coordinates, spatial coordinates, and the neural network estimates it everywhere. So we don't need to have a lot of data from, unlike in the simulation when we have a lot of data and then interpolate the point and the value of few in some points which is not on grid. Then we don't need so much of data, and these networks are typically much smaller than the data from classic simulations. Yeah, and how you can think about physically informed neural networks is that you have some boundary conditions, some measurements, and if you know imagine that relation between pixels are given for some equations, neural network can fill the equation, fill the inside with relevant values. And we also can easily use some known measurements. So this is not present in standard computational methods in physics. I mean, you can do it, but in physical informed neural networks, it is very straightforward. Yeah, and another analogy is that we have some measurements from different angles, like images from different angles, and by optimization of the neural networks, we really can, after this training of physical informed neural networks, we can render new views of the scene, which means that we can approximate a point in approximate the value of the function in any points we know. And here is a cartoon showing the comparison of neural networks with classic neural networks. So the red is the true solution, and green is neural network approximations. So if we don't have a lot of data, they're quite sparse, like here. With classic neural networks, we risk that the network will be very close to the true solution at the data points we have, but apart from them, it will vary a lot. We don't have obtain any control on this. Theoretically, we could do physical neural networks without data at all, what is similar to solving differential equations without initial conditions. So we have some general solution, but we don't have this constants, and the the derivative is known, but we don't have initial conditions, so we don't have this uncoded true solution. And with some data, we are able to fit neural networks to both data points and underlying equations. Now let's dive into how physically informed neural network work actually. In our example, I will be using x, y, spatial coordinates and time, and I want to approximate the function u. In the standard approach that we used a week ago for regression, our neural networks takes as the input here three values, returns a single value, which is estimate of u, and compares this estimate with the known u at a given point. It wants to minimize its neural network parameters, so to minimize data loss. And to this we add physical informant loss, which tells us how far we are from the two solutions. So the points we can add, we don't need to constrain ourselves to the data points. We can sample point, and at any point of the domain get the approximate of u and approximate of the derivatives u of any inputs if necessary, and then check if some equation with u, derivatives of u, is met at to this point, at this point. I will show it equations on this little bit later, but what is important here, there's up to two facts that these points can be taken at any point of the domain, and we can get really a lot of them. And the other that we can compute effectively the derivatives of this estimated u over the inputs coordinates. And this is done by automatic differentiation, which was also covered 1 week ago. So that's really strength of this, that we don't need to care how analytically calculate these values from these weights, but with a few lines, I think they are here. No, okay, they are a little later, so I will not. So with a few lines of code, we can compute these derivatives. And of course, in a most common setup, we have two sources of loss. So this is data loss, which comes from comparison with the measurements, estimates and measurements, and the physics-informed loss, which comes from comparison of equations with u and the derivatives on the equations that must be met in the domain or at the boundary. Yeah. So we have more formal view here and more detail. This is the differential operator. So we can take actually all acting out at u and in gamma. It gives a function which consists of derivatives of t and special special coordinates and the secondary derivatives and so on. So typically we have some condition in the all domain, but we also can have some conditions on boundary. So for example, I mean, maybe there's some condition. Maybe you have at the walls you can give some physical conditions which is met at the walls of the area that we are approximating with our neural network. Okay, so of course this is the most simple setup. In some cases we can think that we can have a situation when we have different domains inside our area of interest. So this, of course, this equations can maybe in one part of our domain is one equation needs to be met, and in another another equation. We are not constrained at any point with the number of different conditions. And we can also have some conditions which are required only on a limited subspace of our input space. Yeah, so what we do step by step now more practically is we need to write our conditions. Typically, we need to get a form that operator over U is equal to 0. So here is a simple heat equation in 1D. Thus, the solution is approximated by neural network, and here we'll add a hat on the approximations. The neural networks takes time and space and returns the estimate. And then we have a loss. There's initial condition and boundary constraints. So at each time we can sample NB points, and for this is our data points. So for each, okay, so that probably should be just data, because boundary condition can be either from data or from equations. So here is condition from data, which means that we compare the estimated value of a heat. Let's say that we're estimating heat here, and the measured values, the mean square error, and additionally we have constraint on the equation with derivatives. So as it was said before, we have we can calculate those guys by automatic differentiation, and we can put this estimated values, and also it should be, if the condition is met, there should be 0, so we can penalize with a square error the deviation from this condition. Okay. Yeah, so our algorithm, what we do step by step is having equation as simple as here. We initialize neural networks, what means we just create this usually, and in iterations we sample both data points, but here what it's written with sample collocation points, which means the collocation points are points where we estimate the physics loss. So estimate some points, compute derivatives at these points, and minimize this this value, which is taken from governing equations. Okay, so here's another cartoon for this. Having x and t approximate u, calculate different different values. Here's boundary condition, so it's also we can calculate the spatial derivative normal to the boundary, and add the losses all together and minimalize. With these additions, this is you can of course add different weights to the different terms, or use some methods to weight different terms in this loss. This also not sometimes not so trivial. Another hyperparameter to tune or to deal with by special methods. And here's the code snippet I told you before. So how do we calculate the derivative over t, and derivative, second derivative, first derivative of x, and the second derivative of x? We'll tell about this just in a moment. But as here, just you can see that this is a few lines of code, not much. And loss, and what you also may see, physical loss is derivative over t minus parameter diffusivity times second derivative over x, which is exactly this equation. Let's see. Okay, maybe we need to speed up. We are close to finish. As I told you, with physically important neural networks, you may not only approximate the function u, but you may also approximate the parameter, which is here is lambda, and this is the diffusivity. And you just what you do is you in your optimized parameters, which you give to the optimizer, that are not only neural network weights but also this parameters lambda, any parameters you need to approximate. A slightly more complicated example here, that we have Navier-Stokes equation with velocity of 3 coordinates and the pressure field. How do we implement? I told from before, we know that the U with 3 coordinates, it can be a neural network, so it takes x, y, z, and time, and returns the 3 values of the velocity. And we also have another neural networks which takes special coordinates and time and returns the pressure field. And we have some measurements of the velocity itself. We don't have measures of pressure, but we add these equations to the physical laws. And what turns out that it is not only working, but which is already very good, but it also can accurately predict the pressure, at least the gradient of the pressure, because the pressure itself does not play a role. So the predicted pressure inside this way is very similar to the exact pressure, even though we did not give any information about pressure itself, only by the fluid velocity. Okay, so just to sum up the advantages of PINNs, the can approximate solution functions with physical constraints. Last week we showed that you can approximate any function with a neural network for regression, but this approximation are not by themselves. There are no guarantees they will meet physical constraints. With physical neural networks, we add this. And with physical constraints, that means that we can estimate the predicted value in the whole domain with having much less data than we would need without this information. In comparison to classic computational methods of physics, you can very seamlessly use partial measurements, which means measurements from some parts of the data and any known informations. This is also physical for neural networks shine in inverse problems when we need to estimate parameters. And they does not suffer so much from the cause of dimensionality. So, for example, if our system has many dimensions, I don't have an example here, but in classic simulation methods, then the size, the memory consumption and the size of the data grows tremendously. And with neural networks, we have this problem limited. Okay, features. Good. So what we also may look at that you might notice that the constraints, physical constraints, they are weak. We don't want to minimize the violation of physical constraints, but we do not have them equal to 0. So they are weak constraints. And we heavily use automatic differentiation. We don't approximate the derivatives by sampling of the function and approximate this, but we use the automatic differentiation procedure. Yeah, and we have actually also a kind of list of disadvantages of PINNs. So physical for neural networks in general can sometimes be difficult to fit to certain functions due to spectral bias, which means that they are weak at very fine graded details, and also it may have some optimization difficulties. Also, what was not said so much, this is said, but for each specific measurement, you need to train a new, for each setup, for each experiment, let's say, you need to train a new neural network. So this training process is quite slow. It's typically slower than normal standard computational methods. So this is the, I said about the strengths that it applies better in some cases, but it's also slower. And yes, that's probably this. So this is not a solution that always works. It has some difficulties in being fitted, and that can take time. And for example, let's consider a direction equation, which means that some wave is just traveling. So this is for us, this is a very simple problem, but it is not for neural network. Yeah, I will take this equation as when it fails or it has difficult. So beta is how fast these strips travel. So if it travels slow, the PINN, classical PINN prediction is very good. But if it starts to traveling fast, the PIN fails. And there are methods to overcome this. There are methods to overcome this with a few approaches that I will tell about here very shortly, but just to show you that there are methods for different difficulties. So one is curriculum training, which means that I first train network with slow waves and then train the same network with waves which travel a little bit faster, and so on and so on and so forth. And in this way, it can work in the end, even for for this fast traveling waves. Yeah, and also, well, they investigated a little bit why this happened. And another way is like we may not train, because typically we train network with points randomly sampled from space and time, and instead maybe it's better to first train the network to the first time window and then make also values from more and more time windows. It can be done by hand or with so-called causal laws. So yeah, so it's just a few examples how the tricks you may need to, in some cases, to make your neural network work. Okay. Yeah, and some other enhancement. We are quite late with time, so I will not stop at this. And also the one weakness is that in traditional solvers you know how much do you have the error, and you know more or less what to do. So you can calculate the error you are making, or estimate at least well. Whereas in neural networks, if your model does not work very well, you have multiple ways, much more ways. In both cases you have, but much more ways you can go. So you can change the model, you can change training, you can add some tricks I told about. So, and you don't have guarantees on your results. So much. Yeah. Okay, I think so. Yeah, and last word in this lecture. So we don't use any package for physics informed neural network, but in your work you may use it, might find it very useful, and a number of them. And you can also find a lot of useful tutorials in them. So you may find a problem which is similar to your problem and modify, and in this way go much faster in research. So this is DeepXD, the most popular, but maybe do not go all in this. Just have a look at many, because there are many of this. I found other frameworks more user-friendly. The second example, the last example today, will be from Torch Physics. The modules is a library from NVIDIA, so this have a powerful also sponsor developer who implements many these tricks inside. And neural methods have some additional also features, like some features from control and so on. Okay. And some tutorials. Take a look after workshops, and you can contact us. Grzegorz Gruszczyński is looking for from people to collaborate. We don't I'm from Center for Machine Learning. We not offer so much, maybe master studies, not PhDs, but we are open to collaboration, and we can also maybe help with some problems if you have. Okay. Are there any questions? Okay, if not, I will make, okay, I have what if equation. I have a question here. What if our equation, we have some non-differentiable expression to output data in NN? To prevent the gradient explosion, they need to be replaced with something else. There are other tricks. Okay, if we want to use automatic differentiation, of course, they need to be differentiable, at least in some domain. And they don't need to be differentiable in the whole domain. So, but if there are other tricks, well, actually it's not so much clear for me if what is the case here. But from my knowledge, this is mostly what you do. You either compare your data or the derivatives which you calculate. So you can follow up my answer and make Szymon, if you add the comment. Okay, so let's have a 5 minutes break, and after this we go to the workshop. And to the workshop, okay, to the workshop, I will show you this. There are two ways to go in. One is from our website at Center for Machine Learning. You can go here, or just copy this this address. So here we are, day 2, and let's meet 9:55. Okay, I think we can start. Let's start with the first notebook, and this is about differentiation, automatic. So yeah, we may open this in Colab. And this notebook is actually mainly repetition from the 1 week ago. It's good that you will understand what's going, but also if it's too fast or something that's not, well, it's not so crucial, I think, for the next step. I mean, it's important to understand. It's good to understand this, but in future you will have just functions which you see this differentiation and don't need to understand exactly why this is here. You can read about this later. Okay, so as an example, we have a function of two variables, x and y, and with automatic differentiation we can differentiate them at various points. Here are the tensors, and for differentiation we need to have required grad equal to true. And PyTorch, once this is enabled, builds a so-called computational graph. I will not go in details here. I think in Szymon's presentation it was more detailed. And the most important is how it works. So we have these grad functions, and they are activated once we call the backward. And this is f, and okay, and we can activate the differentiation with respect to the result by backward. And the backward works to work it well. We need to, the f is a tensor with different values. So the first value is okay, so let's x and y here. So the first value is f of 2 and 4 and so on. This value is for f of 3 and 5 and so on. And to differentiate this well, we need to first sum the output tensor f. This is called a summation trick for gradient calculation. And once we have this, we can have the gradients of x. So for example, this is a gradient of f of, so the first term is a gradient of f of the derivative of f from 2 and 4 with respect to x. And here's the gradient of this 2 and 4 with respect to y. Yeah, so sorry for going quite fast here, but I want to be more or less on time, and this is repetition. And what's important, what we'll use here for this physics-informed neural networks is another way of calculating gradients. I mean, underneath this is the same mechanism, of course, but unlike using backward methods, we can use auto-grad-grad method. We have the same calculations here, and now we'll calculate the derivative of f with respect to x, but without the backward. So we need torch auto-grad-grad. What we differentiate f by what x, and this is the shape of the gradient outputs. This is the weights, so not so much important for our here. It's just always in all examples and application. I was looking for this just torch ones like the value we are taking derivative of. And we also yes, this is also this create graph true, which I will tell about in a second. And this is the f of x is a tensor with derivatives which are the same as derivative x grad. This is the same values. And unlike before, the grad is empty. We don't have this. In order to take the second derivative, we first of all needs to in order to take the second derivative, the first derivative, we need to have create graph equals to true. And we can do the same differentiation on f of x by x. We don't need to create graph anymore because we don't need higher derivatives. Now, just a few words about this retain graph, create graph, and so on. To show it better, let's add another mixture term to this equation. And we have, we'll comment create graph, so create graph equal to false, and see what happens. find out that f of x is calculated well. But if we want to calculate derivative with respect to y, or it's really y, never matters. It's false, and it even visually said that retained graph equal to true, because otherwise, no, the necessary gradients are forgot. So okay, so now let's. It's okay. And it tells retain graph equals to true. It does not say create graph. So let's put it here. We have f of x, and we have f of y, and f of y is calculated, recognized. But if you try to use higher order derivatives, you will fail. So if we want to create higher orders derivatives, we need to do this create graph equal to true. Okay, just maybe that last thing to show you how it's once like. This is what is this? If you are not familiar, this is just an array of ones with the same shape as the input x. Okay, so just to be very quick, that's all. Do you have any questions now? Okay, so let's go to the other notebooks. Okay, now we'll deal with a real problem, real physical problem, and implement physical informed neural networks. Actually start with neural networks which is not physically informed, and then proceed to neural networks. This is the second notebook. I closed previous session because you can have only one GPU CUDA session and the collapse. So if you have active the previous one, you will not. Okay, this is even the CPU. We'll see. Maybe it's enough. This notebook is based on these notes, and it is made by Grzegorz Gruszczyński. What we are going to simulate is this damped oscillations. Not overdamped, but damped is a spring which has some damping coefficients, so we have some oscillation, but they are damped. Which is the equation that physics people know very well, with acceleration and damping and force. And you may notice that there are two parameters, mu and k. One is the spring constant, and one is damping. And you also have mass, but we will remove it here. So we can simplify this with two other so to make it dimensionless with two other parameters, one which is delta and one is omega 0. Delta is connected with damping and omega 0 is connected with spring constant. And we also have some initial conditions for the and U is the position. U here is just the position in the vertical position of the mass. We have initial conditions for the position and for the velocity. This equation has quite simple solution, which looks as you saw above as stamped oscillation and is given mathematically like here. I think A should be 1 because this is the initial condition. And in this task we'll use only as we said before this neural networks, the physical informed neural networks you train typically for specific parameters. For in one experiment, I have one set of parameters, and if I change experiment, I need to train my new neural network. There are some approaches to limit this, but basically that's the use case. You can change afterwards these parameters to see how the system behaves. So first we'll learn the system using normal neural networks. We'll make basically a regression as you did with Szymon ago. Second, we'll learn the system using physical informed neural networks, where we'll know initial conditions and the equations with parameters. And in the next notebook, our data will be noisy, and we'll also not know the parameters in advance, but we would want to estimate them from data. Here's a little function which for delta and omega 0 and time array gives equation. So here's this delta and omega 0, and which are numbers, and TS is an array, and we'll get the position at this is an output position at these times. And below we have a neural network, which is pretty much the same as you had before. Let me know. Okay, this is the form of the neural networks is similar. Basically, you also used sequential, but you used sequential in only one attribute. And here, like 3 attribute first, which is input layer, which takes input and embeds in a hidden dimension. Then you have the inside, the middle, which may have many layers, many hidden layers, and then the final layer. You could easily also write this in the same way as you written the neural networks in the example one week ago. So this initialization, we defined what layers we have in neural network. You could put here, the architecture of like single architecture without splitting this into three pieces, and then we just execute y by one all of this layers, or all of these blocks. We can say these are little blocks. And FCN is a fully connected network acronym. As we said here, the d and omega 0 parameters, we get the time points which are equally distributed between 0 and 1, and we have the exact position by using our exact solution function. We also have some function to plot. Okay, so let's okay, let me see one more. Okay. Yeah, we initialized network as before. The network has one input time, one output, which is position, 32 hidden neurons, and 3 hidden layers. In the optimizer, we put the parameters of the neural network. And we'll learn, and what we learned is okay. Let's see. This is the our target. Our network. Let's see it in the training loop. So we do zero gradients. We calculate losses for the given true time, and for this true time we predict position of neural network, and the loss is mean square error loss, difference between predicted position and the true position. Then loss backward and step the optimizer and making plots from time to time. So here are the time for which we have the data, and here we have the true position. And in each iteration, we'll use all the data we have. Exact training data are in pink, and exact solution are gray. Neural network will fit quite quickly to the to the solution. Okay. If there are any questions at this point, because this is the standard neural network, and we'll go to the physics informed just now. Okay. Let's go to the physics informed training. And this, in this example, we'll do it differently. So, unlike here, when we had this so many measurements, we'll not have all of them. We'll have just the measurement at the initial point, measurement of the time, of the position, and measurement of velocity. And in all other domain, we can use collocation points. So we can check if the approximation of neural network meets the physics conditions we have. And the network itself will be the same as before. So neural network estimate for a given time, estimates the position of the mass. And loss function will consist of 3 elements. First element is the data loss for initial time. So for t time equal to 0, we'll want to meet the initial condition, which is 1. The second term is the initial condition for velocity. So what means that derivative over t of this position at time equal to 0, we need to have to be equal to 0, and the 0 and 1 are given by the initial conditions defined before. So this is for our measurements, initial measurements of this. The lambda 1 and lambda 2 here are the weights of the loss terms, because in general the loss consists of multiple terms. Each term may be more or less important. It also depends how large it would typically be, because we don't want to be the loss to be to consist mainly on of one term, but we want the terms to be balanced. So the second term is the initial condition for velocity, and the third term is the condition for the physical equations. So the governing equations, let's go back up. The governing equations is like this, and so we would check at different points if our derivative of our approximation u meets this criterion. And this is here. So this should be equal to 0. So because it should be equal to 0, then the square of this is our penalty. This points where we estimate the physics loss is called collocation points. You may observe the network is the same and the optimizer is the same. And what we do here is what we make these collocation points equally distributed over the domain, and there are 30. So they are in the same places as the points here, which may be a little bit misleading, because they are not. We don't have actual measurements here, but we only check our conditions here. And in this example, we do this collocation points in the most simple way, because they are linearly distributed, uniformly distributed, and they are unchanged. More typically, you would just sample this collocation points at each iteration, training iteration, from another points to ensure that this is met everywhere. And in more advanced schemas, you would sample these collocation points in the places, more often in the places where you see that the network has difficulties in estimation the true values. So because typically in many physical systems, there are part of the domain which is very easy to estimate, and some often small portion of domains which are difficult to estimate. So in more advanced schemes, you would sample much more densely the collocation points in these difficult parts of the domains, and that probably would be like the standard nowadays to do the collocation points. But anyway, we have, just to keep it very simple, equal to linear distributed and only 30. Yes, and how do we calculate? Because yeah, let's see at the training loop once again. So loss, physics informed loss. Okay, so this is so this is loss we have. How do we calculate? Based on the collocation points and the boundary, which is equal to 0. So we have here this three terms. First is the initial condition loss. We estimate at the time equal to 0 and compare it to the value we know from the data. this is these two lines, and in these two lines we have the second term of the loss, which is the condition for the velocity. We calculate derivative of position over t. This create graph. This create graph would be needed because we would later use the second derivative and calculate, and we because this velocity at points at time t0 should be equal to 0. And first, the third point, which is third term of the loss, which is the physical loss. We calculate the first and the second derivatives of u. So this is velocity, and this is acceleration, and the loss is given by acceleration plus mu time velocity plus k time position. This should be equal to 0 from our physics knowledge, and so because it should be equal to 0, we can square it and use it as the loss. We also set the lambdas. As I said, the lambdas, wow. You may set it for 1 and see if it works, and then iteratively improve. Or do some methods which are also developed to balance them more dynamically. Here we just set it as here. In this example, actually, I'm not aware how much it will change if you the result will change if you change them, because sometimes in some setups, if you change the lambdas, the network will not converge to the right solution. So you may experiment and see if it works. Yeah, maybe let's start it here and tell a little bit more. So let's look at the graphs. The graphs is different. So these points, orange points, they are collocation points. They're not points where we have data. With only data points is here at the very beginning. And what we know from experiments that you have not enough these collocation points, you may go to you may fit to the trivial solution that also, which is the position always equal to 0, and the velocity and position always equal to 0. It evaluates only the initial conditions, but if you are unlucky or you have this lambdas wrong, you may end up in this trivial solution. You may also, with this fixed collocation points, they're not good either, because you can imagine that you can have some function that at this collocation points are very equal to very close to 0. So yeah, I mean they may not be informative. The better techniques to use it in real situation. But anyway, you may see that the network did the integration for us, having initial conditions and the equation. They actually did the integration. You may see that it's not the very end. This is not fitted exactly yet, but do just a few minutes more of training, you will get very, very close to the exact result. Yes, so as I told before, depending on the setting, you may need to change the weights. And yeah, in general, you can also split the data in the test, leave some part of the domain or as test or set. Okay. So let's see what happens outside, because the domain. We had a little bit of data. We had much more of the collocation points, and we teach our network to fit well inside these parts. But what happens outside is our physics-informed neural network so smart to go outside to really see that this is this damped sinusoidal sinus. And it turns out that it is not at all. Here are collocation points and here are predictions. So you see, when the neural networks were not trained on the longer times, it's just have some trivial form. And this is because the neural networks typically are smart. I mean, outside the training domain, and we are not responsible for them so much. But in terms of physical informed neural networks, what is the strength that we kind of control, at least partially, the domain we are training on, because we can, you remember, these training points, we are not the points we have data, but just the points we sample. So if in the training we give longer times, and that the collocation points also in this domain, we could expect that as far as the collocation points are available, we have some reasonable answers from the neural network. So that was the second network, and yeah. I will look at my board if some new question appeared, because I don't see them. Okay, Pavel. Well, I expected the PINN would be better than regular neural network and converge more quickly, but it seems that the opposite is true. Why the neural networks at step 8000 looks better than PINNs? Why? Okay, so the difference here is that the physical informed neural network did not have access to the data. So let's compare them again. So this is unfair comparison here we made, actually. Maybe step by step would be a better approach. So the true neural network had all this data at this point. So during the training, it knew what are the values of where the mass is, the position of the mass, and thus it can converge very quickly to the whole domain. But with the neural network, we did something much more ambitious. So we had the data only on the very beginning. We had this little data points here, and we did not have any data here. The points, the collocation points, are our points that we add during the training, but we don't know the exact position. But we only know that at this point, our equation should be met. Yeah, one fine experiment that can do that I think is very informative is that you can try to, in this setup, try to erase some points from between like 1 or 2 oscillations, and then try to fit normal networks which is not physics informed, and it will interpolate somehow in between very badly. I mean, not without this nice oscillation. Whereas in physics informed neural network, that will fill this hole in the data very nicely. And to make it more comparisonable, we actually should add here not only the initial condition, or maybe we can even omit the initial condition at all, but to give the physical informed neural network both the data points of the data with the same data we had here. So the data point, all of these data points here. Okay, how can I use experimental data in the PINN models? So so this is very straightforward, and yeah, I a little bit regret I did it here. So imagine you have a few points where you measured the true position, or maybe you measured the velocity, and then in the loss you can add another loss, which be like data loss. Okay, I can't write this, but here, but the data loss, which is given like here. So you predict for some t at some times you have measurements, you do predictions, and you just compare it with the measured data. So you can, it is even called loss false. So you can add this term to the loss of physics informed neural networks, and your loss, your final loss would be the sum of the data loss, similar to the normal neural network, and the loss computed here. So maybe the most straightforward way of doing this is okay. You can have here plus some lambda 3 times gets data loss of t data. Yeah, I don't remember exactly if the name is correct and so on, but doing so, your loss would combine the information from the physics and information from the data. Okay. Question from Krzysztof. It seems that PINN learns sort of sequentially. For early stepwalks, the error was larger for time values. It is always the case. It is the case when our problem is sequential. So because we don't have here data, data points are kind of anchoring the predictions to the point. We don't have any anchor here, so we don't know here. So the sequential means because we have one anchor from the data at the beginning, and if we meet the physics equations everywhere, we don't know what does it mean. But if we meet a physics equation very close to the initial data points, it must to follow the true dynamics. So therefore, the true dynamics kind of it's learned sequentially from the beginning, and it is good to handle it depending if you need this, but somehow similar to what's shown here. So if sometimes it's much harder to train with whole time domain at once, you may need to train step by step, either manually or with causal loss, which here is the link. And this also implemented in some of the packages. Because learning based on physics loss, what is very far from the beginning. If you don't know what is here, and it doesn't give you any information. It's just waste of resources to estimate what is here if you don't know what is just in the next instance of time. Okay, Pavel, it is still counterintuitive for me. The physics-based model implemented the loss function provides the data for every collocation point. Yes. It is equally valid outside of the sample range. Yes. So the data in both cases should be equivalent. No. So let's stop here. No, the data in 2 points are not equivalent because in the first case we give them exact values of the position of the mass position at each of this time, and in the second training we don't do it. We did we don't have this because I added. We do have only information that the physics equation is met at collocation point, but we don't have any information about where the mass is at these collocation points. So the first network has much more information. If we add this term, I actually read it here, which directly takes the information about the data. So what are positions of the mass, then the physics-informed neural network would have information both on data and on physics. But now it has information about physics and very little information about data, only at the initial point. And the second, the PINN should be able to just fit the parameters of the physical equations. So it should generalize to the whole domain, including... no, the PINNs does not know the equation. I mean, the neural networks architecture does not know the equation at all. So it's not that neural networks somehow knows these equations and fit parameters. It is very different. This neural networks with many neurons, which is able to approximate almost any function if the network is big enough. So yeah, it's not fitting the parameters, but it is fitting very general function. And the calculation inside is not that you can see at the neural network itself what happens if we give a new time. It goes through this neural network layers. It does not have the equation of motion inside it. The value is estimated with this many additions and multiplications which happens inside the neural network. Okay, Krzysztof. The measurements have been known uncertainties. What are the most popular methods for feeding that into measurement errors and losses? Oh, I think I skipped this. Okay, so yeah, so what if our measurements have uncertainties? The loss function, so you can basically implement it in loss functions. Loss function. One obvious way would be to give a weight to the points where we have the loss function. one obvious method is to give weights to the points, so that now you have this loss is a mean of square errors, but you can have here like weights depending on uncertainty, which is different and known for each point, and then it would put more weight on the points which are we more trust more. And the second way is different loss function terms. Here we have the square loss, but we can, which is actually maybe quite good, which is of course quite good, but we also can maybe tolerate, our loss function does not need to be globally differentiable. It may need to be differentiable only at locally, which means that we can even have a loss function which for certain points does not put any loss unless the difference between measurement and predicted is less than some value of the measurement error. So mean square error also does something like this, but you can modify your loss function to ignore at all the differences between a prediction and data if they are small. So that just a few examples, like most. I'm not expert, because probably people working in depth with uncertainty, they have more sophisticated cases, but like just rule of the thumb that people use is like this. Can we use a PINN with only one experimental data point, and will be traceable? In some cases, yes. And this is actually what we are using here, because remember this, we have in the PINN training, we have only, our data is only at the T0, so only at the beginning. That does not to be at T0, so here is the beginning, but we can also, and you can check this, that there will be some data here and some data here. Yeah, probably you need at least 2 points due to the number of dimension of freedom, but you can imagine that you have 2 values, so maybe you don't have measurements of velocity, but only have 2 measurements of position into 2 or 3 places, and you can check it may work. I mean, it's yeah, should work, but it should work. Okay, so let's go to the last notebook from my side. This is inverse problem, and this is very similar to what we had before with physics form, but we want to estimate, and actually I need to find if we want to estimate both delta and omega, only one of them. Here all the same, so don't worry that I'm going fast. This is the same as before. And okay, so this is inverse problem, but also with our data will be a little bit noisy, because this is like most real data look like. I mean, still nice for real data, and it's also noise, but are also not equally distributed. And what we want to estimate is mu, which is the parameter connected to damping. Mu, which is connected to damping, yes. What we do if we want to estimate some parameter, see what's this to explain. here is how do you do normal tensor filled with 0. So that's because this is only one value. So this is one, it has length 1. It requires grad to become parameter. And in order to optimize something, you need to make it a parameter, which like it's still an object which is basically a tensor, but it can be it's ready to be optimized. So here is what our new is, and to our optimizers we add we concatenate the list of parameters of neural network with the new parameter, which is interpretable, and unlike parameters in neural networks, which are just weights. But this is very interpretable, and we know its real value, which is 2, I think. Yeah, we'll see it later. And we start from 0. You could start from other values, but why not from 0? Now let's see what's the difference. And now it's like we combine loss from the physics, which is the same before we estimate. The physics is the collocation points, is still uniform distributed. And first derivative, acceleration, and loss at these points. And we also have data points. And here, unlike before, our physical informed neural network has observation points. They are noisy, but they are measurements that we have. Yeah, and loss is sum of them with, again, this lambda weight. We'll do backward and step to update weights and update the mu, and we'll record the mu history by appending the item, the mu value. The item is just converts tensor to value. Yes. No, you have some rounding errors, but here it's normally it's tensor, but this is just the value, which does not have this and the, it's also important to read off the values for which the gradient can be calculated, because remember, if we do forward step, that in the background the PyTorch makes this computational graph, and it cleans it for values which are overwritten, for example. But if we keep it, we kind of risk that I'm not sure if without this item that we will keep this computational graph and will occupy our memory. So here's computation. So the physical loss as before, data loss as before, but at noisy data, sum, and write the value of parameter. Here we have estimation, and here we have value of me. It's just filled with 0. So at step 500, we are at 500 here. So we have estimated. So we see that it begins to be initially 0 and then goes up. And then overshoots. Here we are quite close to the true solution already. And after some time, it should converge nicely to the final results. What I can say is that initial value is another hyperparameter to fit. So notice if we can check check others. I mean, it's quite slow, so I don't know if I want to do it. Maybe just in the background. And probably here that would be still okay, but in more complicated systems, you risk not. Okay, it should be float. In more complicated system, you can have issues with this convergence problems. Yeah, okay. Maybe it will go just well. Okay, so this is all in the second notebook, the last notebook I have. So here finally we had this typically combination of physics laws and data laws. You don't have initial condition here. What you can do to play with is wait a minute, because I was thinking about, okay, let's see if that, okay, so this did not converge, maybe yet, maybe not yet. This is a bit strange. Yeah, maybe. Yeah. Okay, so what you can try now, you will see it in the next notebook by Grzegorz, is that the collocation points, they should be sampled in a random manner, at least. And the other way is of finding the difference between physics informed and not physics informed is, I said, maybe not in the inverse problem, but in the forward is to cut some observational data from the middle and observe how physics information allows to interpolate well. Okay, that's all from my side. I just will look at the questions if there are any more. And if not, if there is Grzegorz. I think, let's see, because I think we should meet again at 11. So unless Grzegorz said differently, and so let's meet at 11. Okay, thank you very much. That's all from my side. We're open to the contact. You have the email at the end of the presentation. And good luck with your physics informed application. Bye.
Okay, good. Thank you. So now we'll start the second part of the tutorial for about 2 hours. And here we will deal with the inverse problem with physics-informed neural network. So the goal of this exercise is that we have data, we have the measurements from the, let's say, laboratory, and we are looking to find the coefficients in the equation. So we are actually trying to find the material properties. And in this example, we'll deal with the heat transfer equation, and we'll look for the heat conductivity coefficient. Okay, so this is the heat equation in 2 dimensions. And this is the coefficient which tells us how quickly the heat will diffuse during the simulations. And this is the actual unknown. And we are going to find it based on the data. And this problem will be actually a bit more complex, because we'll assume that the diffusion coefficient is non-uniform. So it is actually a spatial function of the coordinate x and y. So once we write this equation, we have it in the following form. And this diffusion can be also assigned to the more, let's say, advanced thermal problems. So if you look just at the diffusion coefficient, you can also say that it can be viewed as a function of the thermal conductivity of the material, of the material density, and the specific heat capacity of the material. But now we'll just simulate them all together as one coefficient alpha or d. This is the same letter. Now we'll have just a quick recap how these equations come out to us. So we have to realize that the heat transfer is driven by the gradient of the concentration, and the so-called diffusion flux is proportional to the concentration of some substance multiplied by the coefficient of the diffusion. And in our case, we can think about U as being a temperature. And this is known as the Fourier law of the heat conduction. And as we know, the substance diffuses from the higher value of concentrations to the lower. And to have, let's say, matched in the equation, we have to put the minus sign here. And this is proportional to some coefficient, k, d, lambda, whatever, which we are going to find during this exercise. Now, we'll also dig a little bit into the gradient and divergence to be sure that we know how they can be written in terms of vectors. So gradient of U is a two-dimensional vector, and the first term is the gradient with respect to the x-coordinate, and the second is the gradient with respect to the y-coordinate. Other differential operator is the divergence. And actually, divergence is the sum of these partial derivatives. And how to think about divergence is you can imagine that it tells us how much of if you think about the fluid, how much the volume will expand or contract. So this is the meaning of divergence. So, for example, if the divergence will be 0, then we'll have the constant volume. So actually, the fluid will be kind of incompressible. Now, knowing the basics, we can write the problem statement. And it consists of two kinds of loss. First is the data loss. So this is the usual part in a training of neural network. And the second term is the physics-informed loss. So this is the term coming out from PINNs. So here we have the diffusion equation, which we need to integrate over the whole domain, both in space and in time. Now I'm starting the notebook, so have to wait for a moment once it will connect. It imports all the necessary libraries, PyTorch, NumPy, Matplotlib, and so on. The architecture of the network will be pretty similar to the one you have seen on the previous exercises. So we'll be dealing with the multi-layer perceptron, also known as a fully connected network. And here's a short function which will help us to construct such a network. As arguments, it takes the number of the hidden layer, the number of input dimensions, output dimensions, and the kind of the activations functions like hyperbolic tangent. And then in a for loop, this function will create a list of linear layers with a desired activation functions. We have a normalize function to fit the data to desired range, like -1, 1, to is the training. And next we have the Python class, which will store the fully connected network. And again, it takes the arguments as the input and output dimensions, dimensions of the hidden layers, the activations, which is the hyperbolic tangent. And here, common question is not why not ReLU? Does anybody know? Okay, so the actual answer is that when we are dealing with physics, we need frequently higher order derivatives. So this time we will need the second order derivatives, and the ReLU, which is partially linear, will return as 0 as for the second order derivatives. So we cannot use it for the physics-informed neural network at all. This is the actual reason. Next we have the normalized flag and the buffer. We'll have a snippet about the buffer in a moment, but in a shortcut it is just a special kind of special way of storing the variables or the tensors in the neural network object, and it is designed in such a way that once we like save it to the file, then the registers will be then they're becoming a part of the model, so they will be saved all together with the values of the weights and biases. So this is this will be the part of the model, and otherwise, if we save the network to the disk, we will have only weights and biases, and the values like xmax and xmin will be not saved. So we have to register them. And the other thing is that if we move the model from CPU to GPU, then everything would have been registered to the buffer. We also follow this data shift from RAM to GPU memory. And last but not least is the forward method, which returns as the evaluation of the network. Now we'll make a dummy model, and this model will be just to test that everything works as expected before we will read the actual data. So here we've got the dimensions of the domain and time, starting from 0 to 5. And now we are going to create two neural networks. One will one will be responsible for the values of U, which can be interpreted as the temperature, and the second neural network will try to approximate the diffusion coefficient. And the experiments shows that in this kind of a problem, it is better to split the networks into two separate multilayer perceptrons. You can also observe that the diffusion coefficient does not depend on time. So this is also a little bit of a tip to keep it separated. Now I'm executing the cells. Here with batch size 16, I'm going to get some random numbers and evaluate this uninitialized network just to make sure that it is working. I mean that it's taking the argument and it's returning some values. Okay, here we can split manually the X and Y, so the spatial dimensions, and T. So the XYT was such a tensor. XT is XY is without the last column, and T is just the last column. This one is also two columns, so you can write it in this form, I guess. Yes, it works. Now, the repetition about the buffers. So if we take our neural network and ask about the moment state, you see that we have the list of layers, and each layer has its biases and weights, but we also have the X-min and X-max, which are the buffers. There are tensors, as we have initialized them, and the important thing is that if we move the model to the GPU, the buffers will be also there. Okay, so the X-max is sitting on QDA. Now, if I move the model to the CPU back again, the buffer will implicitly move to CPU as well. So I do not need to write another line of code to move the values of the buffer. They are coming all together with the networks. Good. So we know that the model is working, and now we can download the data for the experiment. and check the data points. So what do we have here? The format is that the first is the time dimensions, then we have x and y being the spatial dimensions, and the values of the unknown temperature in the last column. Now we take a part of this data and we put them into the tensors, which will be acceptable as the input for the neural networks which we have designed. So this is the first network responsible for the values of temperature, the unknown U. Okay, and here we have the input for this network, so the spatial temporal coordinates and the values, the data values, which shall be learned and then returned by the network. Next, we define the data loss, which is just the mean square error, and we can test whether it works. So we take a bit of this data, we've got some predictions, and next we can evaluate the data loss. Now we have to assemble the physics-informed loss. So you will need to use the gradient and divergence operator to construct the partial differential equation for the heat transfer. Here we have a gradient operator and the divergence operator. You can write them by your own using just the autograd as on the previous exercises, but here's a convenient function which we found on the Torch physics repository, and it can be used to evaluate the gradient and divergence. And without digging into details, we'll just check how they work. So let us assume that there is some function x cubes plus 1/2 of y square, and we are going to check whether it actually returns, so I mean the gradient and divergence operator returns the proper values. So to do so, to check it, I create the x and y tensor having values 1, and I instruct the PyTorch that will require the gradients of these tensors. Next, I evaluate my function, and now after that I can compute the derivative of this function with respect to x and with respect to y. So the derivative with respect to x is 3 times x squared. So this is 3 times 1, and the result is 3. And the gradient with respect to 1 is 1/2 of 2y. So this is just y. And once I put 1 here, I will get the input 1, I will get the result, which is also 1. Okay, and this is the result, 3 and 1, and it agrees with the analytical expectation. Okay. And next, I will test the divergence with another function. So this function takes 2 arguments and returns 2 outputs, x squared and y cubed. But now let me compute the divergence. so x squared and y cubed, and its divergence is the sum of the partial derivatives. So this is the derivative of the first element with respect to x, it's 2x, and the second element with respect to y, this is 3y squared. And we sum them. This is our divergence. And putting in the values, this is 2 times x plus 3 times y squared. So x was 1, so it's 2 times 1 plus 3 times 4, and it gives us 14. Calculating by hand, and the result from PyTorch is also 14, so everything works as expected. We can also test this function not only on a one-by-one tensor, but also on a mesh grid. Now I'm creating the mesh grid. I calculate the analytical divergence. And I'm going to do the same with the automatic differentiation and test that it works. And indeed, this is the case. So the result returned by automatic differentiation and my analytical result returned the same values on each element of this mesh grid. And I can visualize it and see that indeed the divergence of the numeric, and it's typo, I think. One is analytical. This should be analytic. It looks the same. And here is the plot of the u velocity field. Good. So we have tested our operators, and we can now assemble the differential equation. Once again, the differential equation for the heat transfer can be written in the following way with the anisotropic diffusion coefficient. Or in a shorthand version, like this. And now what we are going to do is that this equation has to be written using the different grad functions, being the wrappers for the PyTorch autograd. So the physical loss function is the gradient of u with respect to spatial coordinates, then divergence of it, and gradient of u with respect to time coordinates. Next, we are going to test whether our diffusion equation is dual works as expected. So we create some random spatial points at which we are going to test this equation at some time with some value. We predict the value of the temperature, unknown u, with the neural network designed to predict it. So it takes the spatial dimension, the spatial coordinates, and the time coordinate. And we also predict the diffusion coefficient with another neural network called model D, which takes only the spatial coordinates, because this diffusion coefficient does not depend on time. And next, we are going to check how close we are to the real solution. So whether it's how good is this equation approximated. So we put these predictions. U, so it's the prediction of the temperature at some xy points at time t, and the prediction of the diffusion coefficient. And this residual diffusion equation residual will return us the value of this equation, and it should be as close to 0 as possible. The closer to 0, the better. Okay, the batch size was 16, and the shape is also 16 of these residuals. So the dimensions are good. And here are the values. And these values are just random because we started with the random neural network. And in the next step, we are going to write the optimization function for it. The loss as the mean value of this residual is 2 to the power 10 to minus 7, which is quite good for the random initialization, but it will be better for sure. And next, we are going to make a sampler for sampling the x and y, so the spatial points in the domain. We define the loss function as the mean square error. We define how many collocation points we are going to use, and the weights for data and physics. Here we assemble the loss as the loss composed of data, so with the weight 1, and to evaluate the gradients. Next, we make the samples for the collocation points. We evaluate our neural networks at these collocation points, and we check the satisfaction of we check the residuals of the diffusion equation and these points, and we evaluate the gradients. Okay, no errors, so we are happy. We move the model to GPU, and we create the actual network for the temperature and the diffusion coefficient. Again, we set the number of collocation points to 45,000. Data weights and physical weights are the same. Number of epoch is set to 6,000. Here we extract the parameters from both networks, so the network for U and network for D, to one list, and we give this list as an argument for the Adam optimizer. We move this in line 8 and 9, we move the model to device being the GPU. We also move data to device, create the list to store the loss. So we will call this list the history. And now in a long for loop, we will optimize this, we'll train this neural network. Good. So in each epoch, we set the gradients to 0 in the optimizer, because otherwise it will accumulate it. We make the prediction for data, and we evaluate the data loss. Then we sample the spatial and temporal coordinates for the physics informed loss. We evaluate the diffusion coefficient and the unknown temperature at these collocation points, and then we check the residual loss and assign with it some weight, and then we sum the total loss as calculate the total loss as the sum of the data loss and the physics informed loss. We do a backward step. Here is a bit of a trick to improve the training. This is clipping the norm of the gradient to avoid too big values. And we check the value of each part of the loss, so the data loss, physics loss, the weighted loss, and the sum of this physics and data loss. We put it in the simple dictionary, and then this dictionary is appended to history. And in each 100 steps, we are going to print the value of the loss function. Now I'm clicking Shift-Enter in order to run the training. Okay, it will run for a while, and perhaps it's time to ask questions. Do you have any questions? Okay, so as there are no questions and we are running the training up to 6000 epoch, let us make a short break till good. So the training has complete. So and the break is over. Here's the value of our loss. Which we can print on the log axis. And now we have a few comments. The first comment is that the physics informed loss, so the orange one, so this is this one, orange, was very small at the beginning. And this is a common case for the physics-informed neural network, because actually if it returns 0 everywhere, then the partial differential equation will be actually automatically satisfied by means of the trivial solution. And this is the reason for the very good values at the beginning. But then this network will kind of decrease in means of the physics laws, because it also have to fit the data, so it cannot put 0 everywhere. And although the physics informed loss is still an order of magnitude lower than the data loss, we'll get the qualitatively good solutions. And once we have done the training with the Atom optimizer, you can do a fine-tuning using the LBGF optimizer, which is a quasi-Newton method, and it will be the second-order convergence. It is slower, but it makes better steps. Okay, first we make a backup in case of doing something wrong. Here's the deep copy method used here. And now we set up the LBGF optimizer. It has a bit of a different syntax than the Atom, so this optimization loop needs to be rewritten. Again, we have the sample for the data, and now instead of the for loop, we have to write a so-called closure. And this closure function will be passed to the optimizer later on. First, we reset the gradients as before. We compute the data loss. The samples are already done, so this can be commented from our previous for loop used by the Atom optimizer. The physics-informed loss is the same. The residuals are the same, and the total loss again is the sum of the data loss and the physical loss, and after which we can compute the backward step. We can print the losses and add them to the dictionary, and finally we pass pointer to this closure function to the LBGFS optimizer. Good. Let me run it. Again, it takes a while. However, I've got the results from the previous session, so I'll continue with them. Here we read the when we read the fine-tuning history into the data frame, and this data frame, and using this data frame format will be easier for us for the plotting. So here's the plotting again, and we managed to get the total loss smaller than 10 to the power minus 2, while previously it was just a little below 1. So we got a 2 orders of magnitude drop here. And next we can make the visualization of the results. To do so, a mesh grid is created. And we know also the exact solution because we prepared this data before using a numerical solver. So this is the real diffusion coefficient. And here's the one which is approximated by the neural network. And surprisingly, it looks pretty similar. And here is the log of the absolute error. Now we'll visualize the temperature. Again, we create a mesh grid for it. Have to do some transformation in order to have a nice to have them in a nice order. And now we will make a plot for each time snapshot from starting from 0 up to 5. So 0, 1, 2, 3, 4, 5 time snapshots. Here's the result time 0. Looks pretty good. Collector is missing. After time step 1. Sorry. And turn off my phone. Time step 2, 3, 4, and 5. So based on it, we can say that the results looks pretty similar. Now some homework exercise for those who are curious what we can do next. For example, we can make a cutout from the data space. So we can see that we can say that our data are incomplete. And in that case, the goal of the PINN will be to find what was in the missing region. So you can use the PINN to find data which are, let's say, missing from or corrupted from the experiment. This one application. Second application is the time extrapolation. We have tried it the previous exercises with Marek, the mass spring damper exercise, and we know that the time extrapolation doesn't work that good for the physically transformed neural networks. We can try different loss weights and trying to do the hyperparameter optimization and to look for the best lost weights. There's also a paper called Neural Tangent Kernel in the physics-informed neural network, which deals with the problem of finding the good weights between different kinds of the losses. We have the physical loss, boundary loss, initial condition loss, data loss, and it's a real problem to find the proper weights between all of these partial losses. Question regarding the ReLU, it has been already answered. And last but not least, set of links for further reading.